you're like in a funky mood and life is making you, classes are driving you crazy, make some bubbles. They reflect the light really nicely. You can watch them jiggle around. You can ask questions about coordinate systems. You can ask questions about changing the recipe, right? There's chemistry here. There's physics. There's math. There's aesthetics. There's ambition and unrealized ambition. You know, you can over-metaphor a bubble, or you can just take it to parties and find a way to have people applaud for you once in a while. There you go. It's warm in here. I had this one, like maybe at the end of class I'll go outside and try it because the cold air really helped it. Somehow it was just floating there. And if you decide to have children, and they will drive you crazy at some point, just make bubbles, and they'll look at the bubbles, and you'll see in their eyes something that makes you joyful. And that's all this stuff is all about, right? I hope I haven't tortured you too much in this class. I do it because I do want you to be successful. And I haze you so you're stronger than the next guy. So, as I said, I'm going to do this for a little while, maybe 3 minutes into class, and then we can play with it at the end of class also. And if you get lucky, I'll slip on my own bubble juice, and class will be over early. It's the last day of class, right? I've gotten to where I wanted to get to. And I will, quote unquote, prove Stoke's theorem in a light way. Okay, come on, one more bubble for the kids. There's my soap film. You can see the water running down it, right? Ah. Okay, once more. Come on, bubble. Come on, bubble. One more time for the kids. There's the hint. We got to go faster. Oops. Huh? The what? Yeah, well, that's the beauty of the dynamics. So, I mean, honestly, well, here we are. Welcome to the last day of class. The boundary changes for that bubble, right? It's kind of fun. You know, it's called surface tension dynamics, right? And you could, you know, as soon as you enclose, you know, assuming there's no evaporation and the soap is not porous, and I'm sure that these assumptions are good on certain timescales and not good on other ones. You know, what happens as soon as you enclose the bubble, all the air that's in there has to be in there until it pops. And the question is, say it doesn't pop, what's its you know, equilibrium configuration? What's it trying to achieve as a configuration? And it's trying to achieve, what it's doing is dissipating kinetic energy by oscillating. It's dissipating kinetic energy. And you kind of have a sense that it's going to turn into a sphere, which is the smallest surface area enclosing a given volume, right? So if you fix the volume, which I've done by closing the bubble, right? It says, well, I have to attempt to create the smallest surface area. It doesn't say it because it's not alive, but the laws of physics drive it to that. And it dissipates kinetic energy into the liquid of the bubble. There you go. Come on, give me stay up there for a second. It's very, very, very wet. So I probably needed less water for this amount of soap. So I would offer it to you guys in the middle of class, but I'm worried too many people would take me up on it and play with bubbles and not pay attention to my last class. So you're welcome to come play with the bubbles at the end of class and outside and, whatever. Bubbles are fun. Be very careful right here. If somebody's bored in the middle of class and doesn't mind grabbing some paper towels, I'm going to hurt myself. And for those of you guys coming in late, this is the bubble, what I call the bubble juice recipe. So today I'm going to finish the conversation of Stokes' theorem, and I'll probably do one more example, okay? And here we go. Stokes' theorem, what was it? Stokes' theorem said the integral over a surface, I think I used sigma for that surface, of the curl of any vector field dotted into the normal vector of that surface, integrated with respect to the surface area element of that surface, is equal to the integral over the boundary of the surface of f dot t hat ds. Okay? And now I think I can do this part of it. One of the comments I made was about the relative direction of clockwise and counterclockwise, and which normal to the surface are we talking about, okay? So from your perspective, think of this surface as being in, it's not going to work. Think of the surface as being in the xy plane, okay, at the moment. So think of the string as being in the xy plane, and when I'm not moving the surface around, ideally it remains in the xy plane. There she be, okay? And so you know that if you were to integrate around that thing counterclockwise, right, and the flux, the left-hand side of that equation of Stokes' theorem, with the flux through this surface, the normal vector is pointing at you. That would be the z direction pointing at you. And that's because we've made a relative choice x, y, z, okay? And that choice is consistent on both sides. That choice is consistent with the tangent vector being counterclockwise and the normal vector being pointing toward you. Okay, so you guys who came late, I owe you a bubble. I'm just taking it easy today. One more bubble, one more bubble, one more bubble. Boom. Not so bad. I've made much, much bigger bubbles. Thanks for the napkins, anybody who threw them down. I didn't notice. So, and one of the points I was trying to make is, if I said that any surface that shares the same boundary should have the same expression. So this you should be able to consider all the surfaces, sigma, that share the same boundary. And when I make this bubble, when I make the bubble, right, there's one surface, there's another. See, here's another that comes this way, and there's another that comes that way. In other words, one that bows out or one that bows in, right? So there's one that when I come this way, it's going to stick out that way a bit, the surface, and when I come the other way, it's going to stick out this way. So it has to be consistent all the time. You have to have the same normal, right? You have to have the same normal. That was the argument, like there's no inside or no outside for this surface. It's an open surface. It's an open surface. Well, I think I'm failing now. I think I've given you enough bubbles, so you guys want more math, right? More math. You want to see a proof, don't you? You all want to see the proof. So the idea is that if I had that hoop, right, let's say it was counterclockwise this way and normal that way, if I deformed the surface, whoop, the normal is going to be pointing in this direction. If I deform it inward, whoop, the normal's pointing inward, right? It's that kind of consistent deformation that says, still, if you're going counterclockwise, according to you, normal's pointing at you. Now, if I deform the surface out, it's pointing still at you. Or if I deform the surface in, it's pointing kind of into that vacuum, that cavity, okay? And that's all the family of surfaces. Now, I wanted to do a calculation here, one example. I'm going to do one example, one physical example, one more physical example, and then I'm going to do a soft proof. Okay? So the example I'm going to do is the following. Consider a simple vector field consider a simple vector field F equals, I don't know, I'm just going to make it up as I go along, okay? Negative y I hat plus x j hat plus x squared plus y squared k hat over 2, something crazy like this. It has no parameters in it. It's breaking one of my cardinal rules, right? My cardinal rules are that everything should have the same units. And this one has units length, and this is length squared. But you've seen these kinds of problems in math textbooks. They play fast and loose with units in math textbooks. Okay, and so let me ask the question, what is the flux of the curl of F through the northern hemisphere of a sphere of radius r, okay? What is the flux of the curl of F through the northern hemisphere of a sphere of radius r? Now, if you were to ask, well, what is the flux of the curl? You write that down first. The flux of the curl is, you take the curl of F, that's a vector field. The flux of a vector field through the surface is the n hat component of that vector field, the normal component of the vector field, integrated over the surface. And so I've been using sigma. I better stay consistent with my notation. This is what it's asking you to compute. If I had to ask you to do that on a computer, it's actually pretty straightforward. You go to the surface, you find all the normal vectors, you evaluate the curl of the vector field, and you dot it in with the normal vectors over all those patches, and you just add it up. Okay? The computation of this is somewhat straightforward. One derivative, one multiplication, and then for each term in the addition, you're going to do it, then you're going to add all those guys up. But the beauty of this is you can use Stoke's theorem. Okay? And Stoke's theorem says, look, this is the integral of the circulation of F around the boundary of sigma. The boundary of sigma. And I used sigma and S over here. Total sloppiness. I apologize. That's sigma and sigma over there, and it's sigma. It's the same surface. It's the boundary of the same surface. Okay? Now, here's where we're a little careful. We draw the hemisphere as such and this is the northern hemisphere, okay? So it's a radius r. And now we're going to use that this is the normal we talk about. If you've chosen the wrong normal, it's not a big deal because it's just going to give you the opposite sign, the wrong sign, okay? It's not the end of the world. But what I really want to emphasize to you is the consistency of choice of normal and tangent, okay? Now, if we were to deform this surface back to this plane over here, okay, this normal would deform to the k hat direction over here. It would be the k hat direction. This other surface, this was the bubble of that other surface, would be in the k hat direction. And looking down in the xy plane, you know what counterclockwise means there. So there you go. There's the tangent vector that's consistent with counterclockwise had I deformed this surface into the plane. Okay? So the way to proceed with the solution to this problem is as follows. Either you go ahead and evaluate this integral. Okay? And in order to evaluate this integral, you have to parametrize the curve, which we know how to do. It's a circle of radius r in the xy plane. Or we recognize the thing that I sort of used already, which is if I deform this surface, I can do it as an area integral in the plane. And let's use not sigma, but d. Okay? D is the disk of radius r in the xy plane. So d is the disk of radius r in the xy plane. the one that's centered on the origin. Everybody's centered on the origin. I haven't emphasized that, but they're all centered on the origin right here. And the point is, I mean, if you really want to go through this mathematically, you would go, the double integral that I want to compute, if you wanted to say without words, just mathematics, you'd write it like this, sigma. By Stokes' theorem, this is equal to the integral over the boundary of sigma of f dot t hat d ds. But the boundary of sigma is also equal to the boundary of the disk. So this has got to be equal to the integral over the boundary of the disk of f dot t hat ds. So this is by Stokes. This is by the fact that the two boundaries are the same boundary. The equator is the boundary of the disk, and it's the boundary of the northern hemisphere. And then the last thing to do is to say, oh, by Green's theorem, so this is d sigma equals d. That's the two boundaries are the same. And then by Green's theorem, this thing is equal to the integral of the over the disk of the curl of f dot k hat dA. And more often than not, this is the easy integral to compute, more often than not. I mean, you know, more often than not in examples that'll be presented to you, okay? But of course, in physical examples in general, they can be arbitrarily general, okay? So, well, that means I have to take the curl of f. So let's take the curl of f. Let's say I'm going to use this method. What's the curl of f? The curl of f is equal to, I'm going to use the determinant way of doing it. I apologize. I said don't use the determinant way of doing it, but I still have to remember with a determinant because that's the one I remembered I learned last, okay? I hat, j hat, k hat, d by dx, d by dy, d by dz, m, n, p, okay? So it's going to be I hat dp dy minus dn dz. So this is, but wait a minute. Do I actually have to compute this whole curl? Yeah, I was about to go into this. I'm like, whoa, save me some time. Thank you, guys. I don't have to do this whole thing, right? I don't need the whole curl. Why do work when you don't have to do work? Save your time to do more different, interesting work. Don't do redundant work, okay? So I only need the k hat component. And that's dn dx minus dm dy. And you'll notice that I kind of chose an easy one. The curl, since it's a linear function, the curl has to be constant. Okay? And so this is equal to dn dx minus dm dy k hat plus I don't care. Right? I don't care about the rest because I take the dot it with k hat, and all this is going to be 0 anyway. Don't do work that you don't have to do. And this dn dx, well, n is x, so that's 1, and m is negative y, so that's minus negative 1. So this is equal to 2, right? And the point here is that, well, that was pretty easy because it's the integral of the disk of the number 2 integrated with respect to a. So that's 2 times the area of the disk, which is 2 pi r squared. That's the power of Stokes' theorem. You can really, really simplify these problems. Now, you're not always going to be confronted with these simple vector fields, but I cannot emphasize enough that these simple vector fields form the basis for all more complicated vector fields. So understanding how things behave on these simple vector fields will actually give you the understanding for more complicated vector fields. If I gave you the, I don't know, 1 over 1 plus x squared times 3x cubed, it's not a fundamental vector field. It doesn't have that fundamental structure that you can sit down and sink your teeth into. Okay. So if you will indulge me one moment of physics here, one of the main places that you will be seeing the application of Stokes' theorem, one of the main places is in magnetism. And what did I say? So this is e.g. magnetism. Okay? So I told you last time that the derivative, the way we see physics, many of our physical laws are written as the derivative of the force equals the source. Okay? What that meant was the divergence of the electrical field equals the source of the electrical field, which is charge density. Okay? In this case, it's going to mean the curl of the magnetic field, so I'm going to write it down. The curl of the magnetic field is proportional to, is equal to, times some physical proportionality constants, the current density, J vector. The current density. So the classic example you're confronted with in magnetism, the kind of the first baby example, is take a wire. Okay? Take a wire. So the wire, and I'm going to look, it's going to be an infinitely long wire. I'm going to look down the axis of the wire. Okay, here's the wire. It's pointing at you. Okay? So cross section of a wire. Okay? And now, current density is charge density times speed of charge. Okay? This is what you expect. Charge density times speed of charge. So what do we have for charge density? It's going to be coulombs per unit volume times the speed, which is going to be something like meters per second. So this is going to be coulombs, if you do this thing, coulombs per second, I'm just rearranging this, meters divided by volume times 1 over meters squared. That's what this is. That's the units of the whole thing. And if you think about what coulombs per second, and this is amperage, this is your amps. This is your amps in your wire. Well, you got a 6 amp, cable or something, wire or something like that. That's the amps. That's the amount that you're pushing through that wire. Okay. And this is the divided by the cross-sectional area. So the current density is your amperage divided by your cross-sectional area. So often you'll use I to be your current, right? That's the number of amps. But what's fundamental is this current density. So how do we actually approach this problem? How do we look at this problem? We do something very similar to what I did with the charge problem. So with the charge problem, what I said is, well, I used an imaginary domain that was outside of my source. And I'm going to do it again. I'm going to create an imaginary domain outside of my source. Okay? Now this is a wire. So you think of it as an infinitely long cylinder of copper. And therefore, it has complete rotational symmetry around that axis. It has complete rotational symmetry, right? Nothing should be different if I rotate around that axis. Because we're thinking of it idealized. It's the only thing in the world at the moment. Okay? So in all directions around this axis, whatever I have as a magnetic field strength should be the same. It could depend on how far away I am from this axis, but it's not going to depend on what angle I'm at. Okay? So what I'm going to do is a very simple problem where I'm going to take this wire and take an imaginary disk of radius. This is the radius little r, okay? This is going to be, I'm going to think of this as the xy plane. We're making cylindrical coordinates for this. This is the xy plane, and so z is coming out at you. K hat is toward your nose. Okay? And what I want to do is just integrate both sides of this expression. Okay? Integrate the flux of the curl of the magnetic field through this imaginary disk that I'm putting around the wire. So let me call this disk D. This is the disk D. And this is the curl of the magnetic field dotted into the normal vector d sigma. Because that is what I'm going to do over any surface. I would do that over any surface. And whatever I do the left-hand side, I must do the right-hand side. So this is going to be equal to the integral over the domain D of the current density dotted into the normal vector times d sigma. All I'm doing is integrating both sides dot n hat d sigma. Okay? And now we have two simplifications in this problem. The left-hand side is the flux of the curl. This is the flux of the curl. And by Stokes' theorem up there, this is the integral over the boundary of D, right, of the magnetic field dotted into the tangent vector integrated with respect to S. So it is the magnetic field vector B, well, sorry, it's going to be B, whatever the magnetic field vector is, B, dotted into the tangent vector T hat. I'm trying to figure out what that magnetic field vector is. On the right-hand side, I've got J dot n hat. We need a moment of understanding the geometry. The current is going through the wire, right? The current is not going this way. It's not going that way. It's coming that way. And the surface normal is k hat, and the current is in the k hat direction. Right? They're both going in the same direction. Okay? So J, so I'm going to rewrite it where I have more board space, so indulge me for a moment. We'll go over here. Please, this will be on the final. This. Bad joke, bad joke. You don't have to laugh at my bad jokes. I know. This will not be on the final. So note, just notice that J dot n hat, right? Well, that's just the magnitude of J. That's just the magnitude of the J vector. Why? Because J is parallel to k hat, and n is parallel to k hat. N is k hat. Okay? J is coming in the k hat direction. N is coming in the k hat direction. They're all parallel, right? So this is J dotted into its direction, which is just its magnitude. Okay? And so the expression for the magnetic field is the integral over the boundary of the domain, D, of B dot tangent vector, ds, is equal to, the right-hand side is just the magnitude of J. Oops, yeah, the magnitude of J. That's all it is, the magnitude of J, dA, the area element. So the sigma, the surface area element in the xy plane is just the area element, whatever I want to do. Does that make sense to people? Well, the magnitude of J is everywhere 0 except in the wire, right? So this is then 0 outside the wire, and it is whatever it is inside the wire. But this is the current divided by the area, the cross-sectional area in the wire, multiplied by the area. So it's just the current. So this whole right-hand side reduces to the current in the wire. Okay? So this, if you want to see all of the gory detail of this, I will work it out over there. Allow me a moment. So just the right-hand side, to emphasize, is equal to the integral over the domain D of the magnitude of J dA, which is equal to the integral over the wire, the cross section of the wire, of the magnitude of J dA. But J is, so what is this? This is the current in the wire, which I'll call I, that's the current, divided by the cross-sectional area of the wire, because that's what I said J was, multiplied by the cross-sectional area of the wire. And so the right-hand side is just the current. And this is all modulo a couple of physical constants, but I want you to see the geometry of all this. So that's what the right-hand side becomes. It's the current. Now let's take a look at the left-hand side. The left-hand side is the integral over this, this circle, so the boundary of the domain, which is now a circle, of the tangential component of the magnetic field, integrated with respect to arc length. Okay? I think I got that right, didn't I? Yeah. So it's like the circulation of the magnetic field. And that's equal to the current. Well, over a circle, right, all the terms in here are at the same distance away from the center of that circle, because it's on the boundary of that circle, right? But I said that this could not depend on where you are along any given circle, because it's completely rotationally symmetric as you look around that wire. So this is independent of angle in here. So this whole thing is just b dot t hat times the length of the boundary of a circle. So this is b vector dot t hat times 2 pi times the radius of that imaginary circle that I created. And that's equal to the current. And what this says is b dot t hat is equal to the current divided by something like 2 pi r modulo some constants of physics. What does this tell me? Well, it tells me actually that the magnetic field swirls around the wire. If I have a wire, right, and I put current through it, the magnetic field is going to be a vector field that points around the wire in the axial direction. So that'll be one reason why we need to learn cylindrical coordinates, actually, to understand that this is the z direction, and this is the theta direction. It swirls around the wire. It's only in the tangential direction. Moreover, it tells me that magnetic field increases the more current you put through the wire. The more current you put through the wire, it increases. And lastly, it tells me if you're outside the wire, the magnetic field decreases in strength as 1 over your distance to the axis of the wire, 1 over r. So you have a 1 over r decrease in magnetic field. Okay? I think we got the 1 over r, what was it, 1 over r squared increase in electrical field, right? 1 over r squared in electrical field, 1 over r in magnetic field. So it was 1 over distance squared for the electrical field, because that was distance to a point. This is 1 over the distance to the axis. So these are the two kind of fundamental problems. The electrical problem and the magnetic problem. They're the two fundamental problems that arise in electricity and magnetism, okay? And so there are two fundamental problems that arise that we use Stokes' theorem for, okay? I'll give you my last little physical example, and then I'm going to do my proof. Just a quick little physical example, okay? In fluid dynamics, so we studied the circulation. I talked a lot about circulation, right? And in fluid dynamics, and this is like in aerodynamics also, by the way. In fluid dynamics and aerodynamics, the vector field we're interested in, F, we are interested in the velocity field, which is often denoted u vector, the velocity field u vector, okay? And the curl of u vector has a name. We call it omega vector. This is a little omega vector, and this is called the vorticity vector. This is the vorticity vector. And so Stokes' theorem gives you a way of thinking about what the vorticity is. We spend a lot of time thinking about the vorticity is. It says the flux through any surface of the vorticity is the circulation around the boundary of that surface. Okay? And Lord Kelvin came up with a great theorem called Kelvin's circulation theorem. And Kelvin's circulation theorem says this. If you start off with a hoop, right, just like some little hoop, an imaginary hoop that you put in your fluid, and you start off with an ideal fluid, so that means no viscosity. So you're like, well, where's that? let's say extremely low viscosity. You start off with that hoop, and you calculate the circulation around this hoop initially. Fluid dynamics will move that hoop around. It'll be over here somewhere else. And you calculate the circulation at any later time, it'll be the same. And that's called Kelvin's circulation theorem. And it's a fundamental theorem to understanding the dynamics of fluids. So I'm not going to get into that too much, but knowing this expression helps you prove Kelvin's circulation theorem. So I'm telling you all of this, and I'm showing you the bubbles because I'd like to try to point out to you that this math has physical, is for expressing physical things, okay? It has physical consequences. And the reason you're asked to go through the calculus process this far is that really you're mostly engineers, you're mostly physical scientists, and you need to have a sense that there's a way to do computations, there's an ordered way to do computations. And I also hope that the way I taught you this quarter shows you that you can actually construct these things yourself by asking questions in a systematic and careful way, okay? All calculus is break it up into small pieces, answer the question on a small piece, and then extrapolate to all the other pieces. Okay? That's really the fundamental thing that's going on in calculus. Now I'm going to give you my soft proof of Stokes' theorem, because that's what you want to leave, with a soft proof of Stokes' theorem. I've got to leave you with that. I'll leave you with a bubble or two. I'm not ever going to ask you for the soft proof of Stokes' theorem. I'm not going to ask you for the hard proof of Stokes' theorem. Okay? I'm not going to ask you for any proof of Stokes' theorem. Okay? But I'm going to try to draw this object here. It sort of looks like that thing in Star Wars where you have the tractor beam thing. Never mind. You guys don't remember Star Wars. There's a movie in 1977 called Star Wars. You would know it. First movie I ever saw in the theater. Okay. This reminds me of the tractor beam thing in Star Wars. You take a surface. And you can break it up into patches. Okay? Little patches. That's what I've done. I've taken, let's imagine some arbitrary surface like the bubble that I sent out to you there. And you break it up into little patches. And so there's a patch, and there's a patch, and there's a patch. You're supposed to get some perspective, right? Tuk, tuk, tuk. Right? Think of tiling, like you had tiled the bubble, right? Or you had some sort of sculpture, then you wanted to put tiles on it. And you think of all those patches, which are the tiles, okay? Now, just stay here with me. Green's theorem. Green's theorem says the circulation of the vector field around this patch is the k hat. If you put this patch in, like, just call this patch in the xy plane. Just put this patch in the xy plane. So, or rather, put the xy plane aligned with that patch. Okay? And Green's theorem says the circulation, the counterclockwise circulation around this patch is equal to the k hat component of the curl integrated over the area of this patch. Right? You're okay with Green's theorem? And then Green's theorem says, just take the separate patch. Don't think of them as being part of the same surface. Go to this patch over here. And you say, wait a minute, I could have put my coordinate system around this patch, put the xy plane over here. Right? Why did I have to put it over here? I'm not thinking about that patch anymore. I'm thinking about this patch. And it says the counterclockwise circulation around this patch is equal to the k hat component of the curl integrated over the area of this patch. So what I've done is I said, wait a minute. I didn't have to have coordinates for the whole surface. I could have done the coordinates individually on each of these patches of the surface, which are flat, right? And I had Green's theorem, which was correct on each of these patches. Well, now, at the boundaries where they meet, just as we talked about how you get cancellation at their common boundary, so too you get cancellation because you're doing the circulation this way around one patch, and you're doing the circulation this way around the other patch. So the circulation at their boundary where they meet cancels out. And then you do that in another patch, and you keep extrapolating over all the patches, and you realize that all the interior boundaries, by patching it together like this, all the interior boundaries, the circulation cancels out at those interior boundaries. And the only thing that's left is the last boundary that's in the surface, which is the boundary of the surface. But if the surface has no boundary, then it goes to 0. And that's it. So you imagine doing this coordinate thing and just patching them together like tiling, and that's the way this whole thing works. So that's the kind of the plausibility argument of Stokes' theorem, okay? If you were to take a more rigorous analysis class, they would actually prove it to you for like good and hardcore, okay? But I would never ask you for a proof like that. But to know how these things piece together, and to know that, oh, I could have chosen coordinates here, thought about this one for a second, pause, erase this one from my mind, then go to this one over here and do coordinates over here separately. And then I just calculate two numbers, which are the circulations around each of these patches. When I put them together, they share one curve, one common curve. But the circulation goes in opposite directions, so that circulation on that curve must cancel if you add those two pieces together. And that creates this cascade where you're left with just the last curve, which is the boundary of the whole surface. Okay, so that's the plausibility for Stokes' theorem. With that, I'm going to say good luck on your finals, good luck in your careers. I hope you enjoy your time as a student. I'm speaking to some of you. I hope you enjoy your time as a student because that's what it's all about. And thank you for your attention this quarter, and I hope you enjoyed my class. And I'm going to make some bubbles. Come and make bubbles with me. Oh, thank you very much. Thank you. Thank you, guys. Come for bubbles if you want. Maybe somebody can figure out how to do this better than I can. If you can figure this out really well, you can help, we can do a show together. You can be my TA. Aw. Hi. We're going to be tested on Stokes' theorem, divergence theorem. Okay. But like 8 is like the, 16.8 is the unified theory, right? I didn't talk in detail about the unified theory. No, we're not going to do that.
Did you get like optional homework and said like it was like study for the actual like test, and I was like, are we having to like know exactly what to do?
Yeah, you just need to know Stokes' theorem and divergence theorem, right? I didn't talk about the unified theory. I didn't talk about the differential geometry. I alluded to it, but you don't need that.
Okay.
It's supposed to just get you excited about math.
Okay.
That's what I wanted to do.
Okay.
So go study it anyway. In your spare time. Because I know you have no spare time. I know you don't. You're a student.